Swayam Prabha. Digital India. Educated India.
Hello everyone. Today we are going to start with module 5. The topics that we are going to cover in module 5 is refraction and the reflection seismology. In the first lecture today, we are going to cover following concepts: introduction, refraction seismology for flat earth, limitations, and then we will be having a summary of today's lecture. I hope you have been liking all the modules that happened so far. And I can easily say that in the incoming modules, you will even like the seismology even more. So the introduction for today's lecture goes like this. Our aim, if you can recall, is to find out the composition of the internal structure of the earth. That means how the physical parameters are varying within the depth of the layers in the earth. So when we say that, we are basically looking forward to see the velocity variations or the distributions and the density distributions within the earth at different depths. So for this purpose, the seismology can help in an incredible manner. And in seismology, we generally record the arrival times of different phases of the seismic waves. For recording so, we use several kind of instruments such as broadband seismometers, short period seismometers, long period seismometers, and many other instruments are available for recording the seismic waves that are generated by a source. These phases, when we record, comes at a particular arrival time. When we have the information about the origin time of the source and the location of the source, then we can probably find the travel time of the seismic waves. The travel time of the seismic waves we can record for the refraction data and also for the reflection data. When we record these kind of data sets such as refraction and the reflection, then we can probably do some kind of mathematical analysis in terms of inverse problem or the forward problem to infer the elastic properties both for the source and the medium. And when we do so, what we generally do, there is a data such as the travel time of the seismic waves, and using this travel time, we can try to find out what kind of seismic velocity structure is there that is producing these travel times of different seismic waves. So basically, if you have the information about the structure of the earth, then using this structure, you can find out the travel times. And this is basically defined in the framework of the forward problem. If suppose you do not know the structure of the earth, you only have the information about the travel times of the seismic waves, then using those travel times, you can go backward. That means using the travel times, you want to find out what kind of velocity structure is there, or the seismic velocity structure, or the what kind of internal structure is there of the earth that is producing those travel times. That we generally do in the framework of inverse problem. Now, a major application of seismology is to find the earth structure such as the distribution of P velocities and the S velocities, and also we are interested in finding the density of the earth. So for this purpose, we record the arrival times of the refracted waves and the reflected wave, and when we do this in a particular framework of the concept that is known as refraction and the reflection seismology. Interest for the lecture today is to understand what are the basic framework of refraction seismology. So in refraction seismology, if we more precisely say, it is concerned about the travel times of the critically refracted waves at the interface of the two medium to identify the depth of the interface, velocity of the layer and underlying half space. So if you look at this particular diagram here, you can see this is the surface at which the source and the receiver is situated, and there is one interface here that is having the reflection and the refraction of seismic waves generated by the source. Now, the principles we are going to deal with in seismology are the Snell's law. Second principle that we are going to use is the Huygens principle and also the Fermat principle. So the ray that is indicated by the red line is basically your direct wave, and the ray that is depicted by the green line, it is your reflected wave, and the ray that is in the purple color is the head wave, which is having the refraction at the interface of the both of the layers. The layer above is having the velocity v0, and the bottom layer, or you can say the velocity of the half space, is v1. Now there are three kind of waves that we just talked about. One is the direct wave, another one is the reflected wave, and the third one is the head wave. So first let's talk about the direct wave. Direct wave is the wave which is directly traveling from the source to the receiver along the surface. And the offset between source and the receiver is basically the distance between the source and the receiver. So if you want to find out the travel time taken by the direct wave in going from source to the receiver, can be represented by TD, which is nothing but the offset divided by the velocity of the top layer. So x is the offset. If we keep the source at the origin at x is equal to 0, then the receiver is at a position at x, and total distance divided by velocity will give you the travel time of the direct wave. So if you will have different receiver at different location along the surface, then you can probably draw the travel time curve for the direct wave. And we have the relation of the travel time that will be is equal to the x by v naught, and the slope of the travel time curve will definitely give you the velocity of the first layer. Now the second wave that we should talk about is the reflected wave, which is indicated by green line, and this is the wave which is having the reflection from the interface and then getting recorded at the receiver here. Because the angle of incident and the reflection are equal, then the reflected wave will be having the halfway between the source and the receiver. That means the reflection will be in the halfway between the source and the receiver. The travel time that you can calculate will be represented by TR, that is as a function of the offset, that will be equal to 2 into the travel time between source and the reflection point. That means the path of the downgoing wave and the path of the upgoing wave. So the distance traveled by this ray will be 2 into x square by 4 plus h naught square to the power under root divided by v naught. And if you will just expand it using the Taylor series, if the x is greater than h, which means x is much larger than the thickness of the layer, then TR square x can be given by x square by v naught square plus 4 into h naught square by v naught square. And this particular equation here will represent the hyperbola in tx plane, and the reflected wave travel time asymptotically approaches that of the direct wave, which means that if the travel time curve, if suppose you have time here and you have x offset here on the x-axis, then the direct wave will be something like this. The travel time curve of the direct wave will be something like this, and the reflected wave will be something like this. So this is your hyperbola here, and this is your straight line here. Slope of the straight line will give you the velocity of the top layer, and this direct wave will be asymptotically reaching to this hyperbola and will asymptotically touching this hyperbola over this point over here. And this particular point here is known as the critical distance. Now let's move on to the third wave, that is the head wave. And this third type of wave is often referred to as a refracted wave and represented by this purple color here. You can see the wave is traveling apart when it's going downward direction. Then it is traveling in the top layer. Then it is traveling at the interface between both of the layer and then going in the up direction before it recorded at the receiver. So in this case, downgoing wave impinges on the interface at an angle at or beyond the critical angle. So if you want to find out the time taken by this head wave in traveling the distance between source and the receiver, then what you can do, you can take the distance that it travels in going in the downward direction and then divide it by this velocity of the first layer and then take the travel time of the head wave and then take the travel time of the upgoing wave and divide it by the velocity of the first layer. The head wave, when it is traveling across the boundary between the two layers, that will be the distance divided by the velocity of the second layer. So that is what we are doing here. You can see the travel time of the head wave is represented by TH, that is equal to x minus 2h naught tan IC by V naught. So if I will extend this line here something like this, then I can calculate the distance traveled by this ray, the head wave, from source to the point of intersection here. That will be given by cos IC, that will be equal to thickness of the layer, that is h naught, divided by this particular term, that let's suppose this is AB. So you can say this is AB, and this implies that AB is equal to h naught upon cos IC. And this distance and this distance will be similar. So this entire term is representing the total distance traveled by this ray, and that is why it is divided by the velocity of the first layer to give the travel time of the downgoing and the upgoing wave. Now it has been added with the travel time of the part of the head wave that travels along the boundary of both of the layers, that is given by x minus 2h naught tan IC. So basically you can see we can find out this portion here. This is, let's suppose this is point AC, then you can write down tan IC is equal to AC divided by the thickness of the layer, that is h naught, which will give AC is equal to h naught tan IC. So this AC if you will find, and we will also extend this line further here onto the surface, then this particular distance you can find out, that is, let's suppose this is your D and this is your E here, then CD we want to find out, then CD can be given out as x minus AC plus DE. AC and DE, because these are same, that is equal to h naught tan IC. So you can write down CD is equal to x minus 2 h naught tan IC. And when you will divide it by the velocity of the second layer, that is V1, then you can get the time for the ray that is traveling from this point here to this point here. So that is what we have done. So the total travel time for the head wave is x minus 2h naught tan IC by V1 plus 2h naught by V naught cos IC. And when we will rearrange it, then it will be x upon V1 plus 2h naught. So value of tan IC and cos IC you can find out from the Snell's law. So using Snell's law, because the ray is coming at the critical angle here, you can see. So what you can write, sin IC divided by the velocity of the first layer V naught, that is equal to sin 90 degree. The angle of refraction is 90 degree because the ray is critically refracting, divided by V1, that is the Snell's law. And when we use it, then we can get the value of sin IC is equal to, because sin 90 is 1, that will be equal to V0 by V1. So using this, we can write the value of cos IC also, that is nothing but under root of 1 minus sin square IC, and sin IC is V0 by V1, so sin square IC is V0 square by V1 square. And similarly, that you can write 10 IC, that is sin IC by cos IC, and that you can get it V0 by V1 divided by 1 minus V0 square by V1 square to the power under root. When you will incorporate this, then you will get this particular formula for the travel time of the head wave. So if you will see this formula very carefully, then what you can probably observe is that there are two terms. One is depending upon the offset distance, that is this one, and there is another term which doesn't depend upon the x value of the x or the offset distance. So what we can conclude is here, this particular value is basically known as the intercept time of the head wave on the time axis, and it is generally represented by tau. And since this is for single layer case, so that is why tau 1 we are keeping it here. So this particular tau value of the intercept time do not depend upon the value of the offset, which means that even though if you will increase the value of x or decrease it, the value of the intercept will remain unchanged, although the first term will keep on changing with the change in the value of the offset. Now, what you can observe from the previous slide is the velocity of the second layer can be found out by the slope of the travel time curve of the head wave. So this particular equation is basically the equation of the straight line, and when you take the slope of it, then it will give you the velocity of the second layer where the refraction is happening. So thus the head wave's travel time curve is a line with a slope of 1 by V1 and a time axis intercept of this much. At some point, however, the travel time curves cross the direct wave, and beyond this point, the head wave is the first arrival, even though it traveled a longer path. This occurs because it travels greater velocity in the underlying layer. So what basically happens is that if suppose when what we are observing here is that first the direct ray will be traveling, that will be recorded at the receiver, and there is this head wave is also coming here, because part of the head wave is traveling in the higher velocity layer. Then after a certain distance, what will happen? The direct wave will not be the first arrival. After a certain distance, because the head wave is traveling in the higher velocity medium, the head wave will be the first arrival. So the minimum distance at which the head wave start to come earlier than the direct wave, that minimum distance is known as the crossover distance. And there is a concept of critical distance as well. The critical distance is when a ray that is coming downward, this ray will be having the incident angle, the critical angle equal to the critical angle. The distance at which it will start to happen is known as the critical distance. Now, this critical distance is defined by xc, that is equal to 2h0 tan ic. So although the head wave appears only beyond the critical distance, xc is equal to 2h0 tan ic, where the critical incident first occurs. This arrival is called head wave because after the crossover distance, it reaches before the direct wave. So this diagram is a very important diagram. You can see there are all the three waves represented here on this travel time curve. One is the reflected wave, another one is the direct wave, and the third one is the head wave. For the reflected wave, as we have seen from the equation of the travel time of the reflected wave, it should be a hyperbola. So the curve is hyperbolic in nature here. There is this direct phase. This is represented by dash line. And there is this head wave that is represented by dot line here. And you can see from the head wave, which is a straight line, the slope can give you the velocity of the second layer, and the slope of the direct wave can give you the velocity of the top layer. and the head wave is asymptotically approaching towards the reflected wave, that means the hyperbola, somewhere over here, and this particular point here almost touches it, the hyperbolic curve. The distance on the x-axis is known as the critical distance, and where the head wave intersects the direct wave, this point is known as the crossover distance, that is represented by xd. So the critical distance is represented by xc and the crossover distance is represented by xd. So the crossover distance is found by setting Td is equal to Th, that is where the intersection happens, where the direct wave has the equal time that of the head wave. That means this is the minimum distance at which the head wave start to appear first before the direct wave. So we will have to set Td is equal to Th, and wherever this will happen, that distance is represented by xd and will be equal to 2h naught in bracket velocity of the second layer plus velocity of the top layer divided by velocity of the second layer minus velocity of the top layer to the power under root. Hence, the crossover distance depends on the velocities of the layer and the half space and the thickness of the layer. The thing that we must note, that is the takeaway. The slope of the direct wave gives the velocity of the top layer, slope of the head wave gives the velocity of the half space. Now we can extend this idea for the n number of layers. Since we know, let's suppose this is the surface, you have multiple layers, like let's suppose this is one layer, there is another layer, there is one more layer, likewise you have n number of layers beneath. So this is your surface here, this is your let's suppose you can call it n is equal to 0, n is equal to 1, likewise you have n number of layers. Now the travel time curve for a head wave at the top of the nth layer. So let's suppose you have the source and here you have the receiver. So what will happen in this case is that the rays will go down, will get refracted, will get again refracted, will reach to the nth layer, travel as the head wave along the interface, and then it will start coming back and will be recorded at the receiver. Right. So the total travel time for the head wave that is traveling across the boundary between nth and n minus 1th layer will be represented by Thn, that will be x upon Vn plus tau n. This is the intercept time. And if you want to calculate the intercept time for the nth layer, then it can be calculated by using this particular formula or the expression, which is analogical to the layer over the half space case. So that will be tau n will be equal to tau sigma j is equal to 0 to n minus 1. That is hi layer, that is thickness of the jth layer. It should be, I think, j. Then 1 by vj square minus 1 by vn square to the power under root. So what we can do is, suppose if you want to find out the thickness of each of the layers from within which these rays are traveling inside, we want to find out the thickness of those successive layers. So what we can do, we can use equation of either crossover distance, or we can use this particular equation to find out the thickness of each of the layer. So how we can do, let's suppose if you want to use this particular formula. So when you do your experiment for refraction seismology on n number of layers, then you can probably get curve something like this. Let's suppose this is your travel time curve. Here you have t, here you have x distance, and let's suppose this is your direct wave, and from the first layer, this is your first layer, and the travel time, for n is equal to 1, the head wave that is traveling along the boundary between the first layer and the second layer will be having, let's suppose, the slope something like this. This is for n is equal to 1. Since the velocity is keep on increasing downward direction, the slope of the head wave, that means the wave that is traveling across the interface of the various layers as you go deeper, the slope will get shallower and shallower. So for the second layer, the slope may be something like this. For the third layer, the slope may be something like this. Likewise, for nth layer, the slope will be something n is equal to n. Okay, so that is n is equal to n minus 1. So you can see that the slope is getting shallower and shallower. From this, if you will extend it further onto the time axis, then you get the intercept time for the first layer, that is tau 1. Likewise, if you will extend the second, n is equal to 2, then you will get the intercept time tau 2 here. Likewise, for third one, you can get intercept time tau 3 likewise. So what you can do, if you know the velocity value of the tau for intercept time, and also from the slopes you can get the velocity of the top layer and the layer beneath. So using the iterative techniques, you can find out the velocity h0, and then you can find out the velocity h1. This is the crossover distance xd. Crossover distance you already know, where the direct wave and the head waves are intersecting with each other. This particular value you will get to know from the record section, and then you can keep on doing this work. So like for the second case, you can do the xt is equal to 2h1 v2 plus v0 divided by v2 minus v0 to the power under root. Likewise, this will give you the h1. Likewise, you can keep on doing it up to hn minus 1. So that is how you can get your thickness of each of the layer. Using the equation 1 also you can do the same. Since you know the intercept time for each of the layer, then you can calculate, you also know v0 and v1, so you can successively calculate the value of h0, h1 and h2, likewise hn minus 1. This is what it is represented in this particular formula. It says that the thickness of the successive layers can be found by starting with the top layer, whose thickness h0 is given by equation 1 and 2, and continuing downward using the iterative formula. So this is the formula using which you can find out the thickness of successive layers. Now this is the case of two layers over a half space. This is layer 1, this is layer 2, and there is a half space here. The velocity of the top layer is v0, the layer in the middle is v1, and the half space velocity is v2. The thickness of the top layer is h0, and thickness of second layer is h1. Now you can see there is this source here, and from the source the ray is getting downward and getting reflected and being recorded at the receiver. Likewise, there is a head wave here also. This is the head wave here that is going and traveling across the interface of first and second layer, and then going upward and recorded at the receiver. Likewise, the reflection and the refraction will happen for the second layer also. And when you will draw the travel time curve for both the reflections, both the head wave, that means h1 and h2, and reflections r1 and r2, then you can draw the travel time curve. So what you will observe is that this is the direct phase, that is here, and for the top layer the head wave is this one. This is the head wave for the top layer, that means at the intersection between the top layer and the middle layer. And then this is the head wave for the second interface, and these are the reflection hyperbolas. So this is the reflection hyperbola here is for the R1, and this is the reflection hyperbola for R2. Using this travel time curve, you can probably find out the velocity of the V1 and V2 from the slope of H1 and H2, and wherever they are intersecting with the direct phase, that will give the crossover distance. Using the value of the crossover distance and the formula, you can probably find out what is the thickness of h1 and what is the value of h0. That is what it is written. Ray paths and the travel times for a multi-layered model in which velocity increases with depth. Each layer gives rise to a head wave hi, whose intercept on the time axis is tau I, and a reflection ri. The direct wave arrival is also shown. The different phases are shown in this particular ray diagram. Now let's talk about the limitations of the refraction seismology of flat earth model. So first thing that we must need to understand, why we call it a flat earth model, why we are not calling it a spherical earth model. because the flat earth model case is the good approximation in case of we are doing shallow earth seismology. So suppose if you remember, as per the Snell's law, it says that the ray parameter remains constant along the path of the ray, which means R1 sin I1 by V1 is equal to R2 sin I2 by V2, where R1 and R2 are the radial distances at each of the point of the ray path. In case if you are working or doing your experiment for the shallow earth, which means near to the surface of the earth, in that case what will happen? The R will not change significantly. The R1 and R2 will be almost similar to each other, and that will happen only in the case because you are considering the shallow earth model. So in the case, so shallow earth is basically considered in the case of oil and gas exploration, or you can say the exploration seismology. So in that case, what we will do, we consider the shallow earth layer, that means the layers that are near to the surface in comparison to the depth of the layer or the radius of the layer. Those thicknesses of the layers are very like insignificant. So in that case, R at each point of the ray in that case will remain same. So R1 will be approximately equal to R2. So R will be cancelled out, and that in that case what it will be remained with, sin I1 by V1 is equal to sin I2 by V2. So that is the Snell's law for the flat earth model, and because the R is same, so the layers will be considered as flat. They will not be having any curvature. So that is what we are doing it here. We are considering the flat earth model case for the refraction seismology here, and you can see we are talking about the limitations. The case one where there is a presence of low velocity zone, which means that velocity are not strictly increasing, which means there is a layer which is having the velocity lower than the velocity of the layer above. Let's suppose this is an example where there is a surface at the top. There is a layer of velocity v1, v0. There is another layer v1. There is another layer v2, and there is a half space of velocity v3. Now, since we are talking about a low velocity layer, the velocity v1 is smaller than the velocity of v0. So in that case, what will happen? There will be no head wave at the interface of v1 and v2, because v1 is smaller than v2. This head wave will not appear here. So what you will see on the travel time curve, first you will see the direct phase, that is having the slope 1 by v0, and then you will be having the slope 1 by v2, and 1 by v1 slope will be missing. That is happening because there is no appearance of the head wave in the case of low velocity layer. This is the first limitation. The second limitation is when the layer is too thin or has a very small velocity contrast. So that means the velocity difference between v0 and v1 is very small, or the layer is very thin. So in that case, what will happen? The velocity of the slope associated with the v1 velocity will be there, but it will not be possible to identify that particular slope. That is what it is written here. Another problem occurs if a layer is thin or a small velocity contrast with a 1 below it. Although a head wave result, it may never appear. So this is the summary of today's lecture. A major application of seismology is the determination of the distribution of seismic velocities and hence elastic properties within the earth. Refraction seismology is concerned about the travel time of critically refracted waves at the interface of the two medium to identify the depth of the interface, velocity of the layer, and underlying half space. The travel time of the direct wave is x upon v0, that is offset divided by the velocity of the top layer. The travel time of the reflected wave can be calculated using this expression, and for the head wave it can be used the expression that is written here. The thickness of successive layers can be found by starting with the top layer using this expression that we have seen using the equation 1 and 2. Either equation 1 can be used, that is the intercept time equation, or equation 2 can be used, that is the crossover distance formula. That is all for today. In the next lecture, we will see the case where the layers are dipping. These are the references, and thank you so much. Bye-bye.